Hey folks, in this video we're going to be talking about heat, enthalpy, and reaction enthalpy diagrams, and Lord, I would love to be eating a bagel right now. So we got a few objectives here. I would like you to be eating, no, I would like you, man, I'm really fixated on that bagel now. I would like you to be able to define heat in the chemistry context. I would like you to be able to explain the relationship between heat, temperature, and energy. I would like you to be able to define enthalpy, which is a funny word, endothermic and exothermic. I would like you to be able to interpret a reaction coordinate diagram. And holy cow, define activation energy. We got a lot on the table. Let's get into it. Heat, temperature, and energy. Well, heat, which we're going to use Q as our symbol, a lowercase q as our symbol for heat in chemistry. If you want to beef with me on that, tough. That's just how scientists have done it. This is related to thermal energy and kinetic energy. In a previous video, last video, I said that heat is basically the same as thermal energy, but that's not actually true. Heat is actually the transfer of thermal energy between two chemicals colliding. So when thermal energy moves between things, that's heat. So I guess you could say that heat is thermal energy. I don't know. There's a lot of different definitions out there. If you want to say heat is thermal energy, I won't fight you on that. Ever. So during a collision, chemical energy can be converted into thermal energy and transferred. So when things collide, a little bit of heat is going to be generated and transferred between these two colliding things. Not generated so much actually, but it's going to transfer between the things. It's that kinetic energy is going to turn into that thermal energy. And so thermal energy can then also be transferred to a chemical. So maybe this guy's got a lot of movement and it boofs this other guy. Well, that boof is temporarily going to be thermal energy and then turn into kinetic energy and move this sucker away. It's a little confusing. If you're feeling confused, that's normal. The chemical with more kinetic energy is going to transfer heat to the other chemical. So this guy's moving around real slow, and this guy boofs that sucker in. It's going to transfer that kinetic energy into this other one as heat, and then this guy's going to get that heat and move away faster. Anyway, let's get off that weird Q heat stuff. Temperature is a measure of the average kinetic energy in a sample. We've talked about this before. If you go back to the particle theory video, we know that particles move faster, and that corresponds when fast-moving particles, ones with a lot of kinetic energy, have a high temperature. We know temperature is related to kinetic energy. Beautiful. So things with high temperatures, yeah, have lots of kinetic energy. Well, temperature and heat. When you touch something cold, let's think about this. The cold thing has less kinetic energy than you. We know this. It's cold. It's got a low temperature. So when particles in your hand, start colliding, interacting with that cold thing, they're going to transfer heat to that cold thing. They're going to take away some of your kinetic energy and add it to that. You lose that kinetic energy, the thing gains that kinetic energy, and you feel cold. Your temperature will decrease. Oh, face, get out of here for a second. Your temperature will decrease when you touch that cold thing. When you touch something hot, it's basically the opposite process. When you touch something hot, for instance, if you grab a hot pan handle, I don't have a scalding hot pan handle to grab right now as an example, but if I touch that, there would be collisions between my skin and the pan handle. And it has a high kinetic energy, at least inside relative to it. It's got a lot of energy. And so when we start colliding, it's going to be transferring heat into my hand, little particles inside of my hand. And yeah, the temperature of them will start to increase. And I might get burned if I hold it for too long. All right, heat and enthalpy, another weird word. Enthalpy, we're going to define it with the letter H, is the total internal energy of a system plus the product of the pressure and volume of the system. We got this funky equation. Enthalpy equals energy plus pressure times volume. And a system is a term we're actually going to use a bunch. Let's talk about that. A system is a collection of items or chemicals. So if I'm studying a reaction, it's usually going to be inside a container. That whole container and whatever chemicals are inside would be the system that I am studying. Everything else would be the surroundings. But the system is whatever stuff you are interested in studying. So this could be, yeah, a balloon full of air. It could be the moving piston inside of an engine and the chemicals inside of that piston area. That's a cool system to study. It could be a fire inside a wood stove. You might study that system, say how much energy is being released by this system as the fire burns. Just the things you get out there. So let's talk about changes in enthalpy, because this delta, we may have seen delta before, I believe we have, but just for clear, delta means change in whatever. So delta H means change in enthalpy, because H is enthalpy. Well, enthalpy is a weird thing because we can't directly measure it. It's only a thing that we can measure changes in it during chemical reactions or physical changes. So one thing we do know, though, is that at a nice constant pressure, our change in enthalpy is the same as the heat flow. So the heat that goes in and out of something during a reaction or physical process is the same as the change in enthalpy. So yeah, enthalpy, change in enthalpy, is the heat given off or absorbed during a reaction. And this is going to be true for most of the reactions we study. Typically, we're going to study things at a constant pressure because we're just going to be under atmospheric pressure. Well, changes in enthalpy, let's talk about that. A positive change in enthalpy. Ooh, fun. Heat flows from the surroundings into the system. The system has a positive change in enthalpy. It's getting that enthalpy or that heat from the surroundings. This means that the energy inside our system is going to go up because we're getting thermal energy from the outside, and our temperature should increase. And that should lead to the energy and temperature in the surroundings to decrease, because if we're going to get energy, it's got to come from somewhere. So this is going to be what we call an endothermic reaction. When our enthalpy increases, energy flows in. We have a positive change in enthalpy. Heat flows in. So we call this endothermic. Endo meaning in, we're going in, and thermic for heat. And so some examples of this would really, I just got one for you. It's ice melting. So when ice melts, heat goes into that ice and it starts liquefying it out of that cold, cold state. So typically in an endothermic reaction, it's going to feel cooler than its surroundings. Like ice feels cooler than its surroundings if it's melting. And it's pulling heat in from its surroundings. So this would be our system, and all around it is our surroundings that we're getting energy from. Neat. Well, if we have a negative change in enthalpy, a negative delta H, that means that heat is going to flow out of the system that we are studying. The Q, or heat flow, is negative. We have less than what we started with, less heat, so it's flowing away. And so this means that the energy and temperature of our system is going to decrease, and the energy and temperature of the surroundings is going to increase, because that heat is going to flow out of the system and into the surroundings. So this is going to be what we call an exothermic reaction. Exo for like outside, like an insect's have an exoskeleton. It's on the outside. Exothermic, because thermic for thermal or heat. Heat flows out. And so a nice example of this would be a fire. Get out of there, little thingy. So you stand next to a fire and you feel very hot. That is because heat is flowing out of that fire, that combustion reaction. And so one thing I always typically remember is that fire has a negative delta H. I don't know, that's helped me remember how to keep this stuff sorted. I'm just like, fire, negative delta H, which feels weird because it makes things hot, and so negative feels weird there, but whatever. All right, cool beans. So let's talk about that just for 1 second. So our fire is going to feel hotter than the surroundings because it is giving off heat. It is exothermic. Reaction enthalpy diagrams. Let's talk about these suckers before this video gets real long. So this is a diagram that shows how enthalpy changes throughout a chemical reaction. The y-axis shows the free energy, which is related to the enthalpy of the system. I don't want to get into how they're different in this video. And the x-axis is going to show the progress of the reaction from reactants to products. Let's take a look at an example just for 1 second. We're going to have a line that shows the energy of the chemicals as they change throughout the reaction. So here we've got a thing. We see where our reactants are and their energy on this y-axis. And as the reaction goes forward, we move from our reactants to our products. And we've got some interesting stuff going on in here. We see that the energy is going to go up over this hill, and then in this case, it's going to drop down. Here we have a negative change in energy. We go down. So this would be a exothermic reaction because we're releasing energy out. Our products have less energy, so that energy has been released. But yeah, that's just what this slide says right here. The difference in energy between our reactants and our products is going to be equal to, or at least related to, the delta H for the reaction. So this guy lost energy, therefore it's going to have a negative delta H, and therefore be exothermic. And so, yeah, this is exothermic because we've got a negative delta H. But if we had a positive delta H, if our energy increased, we would have a endothermic reaction. Well, there's this other thing in here called activation energy, and that's the amount of energy that's required to actually initiate a reaction. So let's think back to my marker and my cap. You know, if I want to put these two together, if they don't have any energy, or if they're just floating around, man, they don't really go together. So if they collide, though, again, we've talked about they need to have the correct amount of energy. If they don't have enough energy, they don't really stick together. So I need to give them the correct amount of energy, an activation energy, in order for these two to stick together now. Neat. Well, that is the end of this video. I hope you understand, or at least have wrapped your mind a little bit around the concepts inside this video, because they're a little bit spicy. Anyway, ta-ta, and have a great rest of your life.